Over 90% of my career was devoted to research in applied nuclear physics related to nuclear weapons, electromagnetic pulse (EMP) phenomena, and how to protect our national defense against EMP. I was the principal scientist and director of large government contracts with the Defense Nuclear Agency, now the Defense Threat Reduction Agency, the Office of Naval Research, and the Department of the Army. All of these EMP efforts involve developing large computer models of the applicable nonlinear physics. At Mission Research Corporation, I worked closely with Dr. Conrad Longmire, the first to explain the magnitude of high-altitude EMP, and who, along with Dr. Marshall Rosenbluth, worked out the details of Edward Teller's first thermonuclear device. In the following slides, I explain the basics of EMP and its effects on critical national defense systems. EMP can cause temporary upset and even catastrophic failure of modern electronics and electrical systems over considerable geographic areas of the Earth. Fixed and mobile ground-based systems, aircraft, satellites, missiles, and naval systems could be affected and therefore must be hardened to these severe electromagnetic environments. Discussion of these hardening measures is beyond the scope of this presentation. Here, only the generation physics and generic numerical results are provided to give a general understanding of the serious nature of nuclear weapon-generated EMP. EMP is divided into three general categories: high-altitude EMP, or HEMP, source region EMP, or SREMP, and system-generated EMP, or SGEMP. For HEMP and SREMP, the electromagnetic fields result from detonation products, X-rays, gamma rays, and neutrons interacting with the surrounding environment. For high-altitude EMP, that environment is the Earth's upper atmosphere. For source region EMP, it is the Earth and its adjacent atmosphere. System-generated EMP, on the other hand, does not occur until equipment is introduced. It is the electrical signal resulting from detonation products interacting directly with the equipment. Because system-generated EMP signals vary so strongly with equipment topology, detailed waveforms of SGEMP effects will not be discussed here. Most of the energy of a nuclear detonation occurs as kinetic energy of the fission fragments. This in turn heats the surrounding material to produce large amounts of X-rays, which in turn, for a surface and air bursts, heat the air to produce the fireball and rapidly expanding air that produces the blast wave. For surface and air bursts, the surrounding material is air and weapon debris. For an exo-atmospheric burst, the surrounding weapon materials are heated to produce the X-rays. However, there is no air to produce a blast wave that significantly propagates beyond the local burst area. We will see later that the expanding hot weapon debris plays an important role in generating a late-time, high-altitude nuclear EMP. A small portion of the energy released in a nuclear detonation is in the form of subatomic particles, and electromagnetic energy in the form of X-rays and gamma rays. When these interact with the surrounding environment, They create free electrons and positively charged ions to produce a highly ionized environment that is called the source region. The gamma rays also produce a current of Compton scattered electrons, which in turn create the large EMP fields. Direct interaction of the weapon, X-rays, and gamma rays with equipment materials produces SGEMP. EMP is thus a generic term that refers to the resultant electromagnetic environments caused by the detonation X-rays, gamma rays, and neutrons. For high-altitude EMP, abbreviated as HEMP, the gamma rays interact with the upper atmosphere in a source region approximately 20 to 40 kilometers above the Earth. They produce scattered electrons by Compton scattering that rotate around the Earth's geomagnetic field lines to produce an electromagnetic field that radiates to the Earth's surface as a plane wave. Because it is a plane wave, the electric field E and the magnetic field H oscillate perpendicular to each other. E divided by H equals the impedance of free space, 377 ohms. Therefore, HEMP is described as a plane wave of electric field strength in volts per meter propagating to the Earth. The coverage of the HEMP field on the Earth is the surface area enclosed in the tangent points from the burst, that is to say, a very large area. One of the first exoatmospheric tests of a nuclear weapon by the U.S. was Starfish Prime on the 9th of July 1962. It was a burst of 1.44 megatons at 400 kilometers above the mid-Pacific Ocean. HEMP from this test caused significant electrical damage in Hawaii, about 900 miles away. It knocked out about 300 street lights, set off numerous burglar alarms, and damaged a communications microwave link. The resulting artificial radiation belt damaged numerous communication satellites, including Telstar. A magnetohydrodynamic, or MHD, pulse is also created by a complicated process of the expanding heated weapon debris interacting with the Earth's geomagnetic fields. This pulse is not a plane wave as in the early time pulse just described. More details of the MHD pulse and its effects will be discussed later. The Soviet Union also conducted similar high-altitude nuclear tests. The effects were of such concern that this and the Cuban Missile Crisis led President John F. Kennedy and Premier Nikita Khrushchev to sign the Limited Nuclear Test Ban Treaty on the 25th of July 1963, banning atmospheric and exoatmospheric nuclear testing. If the nuclear fireball touches the Earth, the electromagnetic fields outside the fireball are within the ionized air region and are called source region EMP, abbreviated as SREMP. The figure shows Compton electrons moving radially away from ground zero in a hemispherical geometry. The Compton electrons produce secondary electrons by ionizing the air atoms. This ionization of the air creates a source region of high air conductivity. As the distance increases, the electrons return to the fireball by entering the relatively high conductivity ground as shown in the figure. This toroidal current flow creates a complicated electromagnetic field. The E field has both vertical and radial components. Because of the toroidal current flow and the significant air conductivity, the E and H fields do not have a simple relationship, as does a propagating plane wave in free space. Although these fields fall off rapidly with distance from the burst, they are significantly larger than the HEMP fields. The radial E field can couple to long power and communication cables as shown in the figure. The resulting large currents can propagate to distant facilities. Significant surge protection at the facility is required to mitigate the effects of these large currents. This is important even for national defense facilities hardened against the blast wave. There are various standards to define the HEMP waveform at the Earth's surface. Two predominant standards are the Department of Defense MILSTD 464D and the Department of Energy standard. A combination of these two standard waveforms is shown in the figure. E1 and E2 come from MILSTD 464D. E3A and E3B are defined by the DOE standard. The DOE standard gives the best analytical model for the late-time MHD waveform. The MIL standard gives the best description of the early-time waveform. This waveform is used in the following slides for a numerical assessment of HEMP effects on power and communication cables. There are three main time regions in the HEMP E field. The early time portion of the field, E1, is generated by Compton electrons created by the prompt gammas from the burst, which interact with the upper atmosphere and geomagnetic fields as described above. The mid-time field, E2, is generated by Compton electrons from slower neutron gamma and secondary gamma ray interactions. The magnetohydrodynamic, or MHD, signal forms the final component, E3. It is driven by the hydrodynamic motion of the weapon debris and the ionized atmosphere across the geomagnetic field lines. The 1 to 10 second time period is known as the blast wave. The 10 to 300 second time period is known as the heave wave. The first of these, designated E3A or blast wave, is due to the expansion of the hot weapon debris, expelling the geomagnetic field and creating a magnetic bubble. The distorted magnetic field lines induce an electric field in the Earth's surface. At later times, the debris in the bubble flows along geomagnetic field lines and heats and ionizes the upper atmosphere, causing it to expand buoyantly and rise. The rising conducting patch crosses the geomagnetic field lines, causing currents to flow in the patch and producing an electric field in the surface of the Earth beneath the patch. This is designated E3B or heave. The two processes occur in different time regimes and have different geographical distributions of the electrical field at the surface of the Earth. Although observed in the 1962 Starfish Prime test and early Soviet high-altitude nuclear tests, detailed models of the MHD signal are from fairly recent research compared to E1 and E2. During my career, the MHD signal was not well modeled and was not included in most HEMP assessment calculations. The later time portions of E2 and E3 strongly coupled to long conductors, that is to say power grids and communication cables, due to their long duration. This is up to minutes for E3B. This induces significant currents on long lines. E1 contains much less propagated energy than E2 or E3. It is important for sensitive electronics, which require shielding and lower-level surge protection compared to the later time field components. Here is an example of the coupling of the above hemp field to a long buried cable. Because hemp covers such a large area on the Earth's surface, the E field is assumed constant over the long line in question. Reflection from the air-ground interface is included in the calculation to obtain the transmitted E field into the Earth that couples to a buried long line. It is important to note that reflection does not apply to the MHD fields because they are modified geomagnetic fields within the Earth near the Earth-air interface. The resulting long line currents induced on the buried cable contain a total charge transfer of about 60,000 coulombs and 33 megajoules of energy through a 1 ohm load. Note that the corresponding quantities in the early time portion of the cable current are only 21 coulombs and 3.9 megajoules. Therefore, most of the energy and charge transfer occur from the MHD-induced currents. Unlike the HEMP calculations in my day, we will see that the MHD-induced charge and energy transfers approach source region coupling to long lines from a surface burst. If only E1 and E2 are considered in the calculations, the results are similar to nominal lightning strokes. The MHD-induced currents have changed everything in the assessment of the threat from high-altitude EMP. The next two slides deal with the source region EMP SREMP from a surface burst and its effects on similar long lines. This slide shows a nominal unclassified radial E field from a 1 megaton surface burst. Notice that these fields are generally larger than the HEMP fields, especially at later times. On the other hand, they do not continue to the extreme late times of the HEMP MHD fields. They are essentially zero at 1/10 of a second and beyond. The HEMP MHD fields continue for several minutes. The SREMP fields at the Earth's surface are within the region of highly conducting air, the source region. They are not plane waves. They are very complicated as discussed in slide 5. They also fall off with distance from the burst. However, the induced currents on a buried cable continue to propagate for large distances. Using the SREM field of slide 8, buried cable currents were computed and are shown in this figure. The currents are significantly larger than the HEMP-induced current. However, they do not persist as long. These long-line currents represent a charge transfer of 6,000 coulombs and 130 megajoules through a 1 ohm load. This is the reason that bunkers attached to long lines entering the burst had extensive electrical damage in the early days of nuclear testing. Both HEMP and SREMP induced currents on long lines are extremely large. They are significantly larger than the largest of lightning strokes, the largest 1% of strokes. They represent charge transfers of thousands of coulombs and many megajoules of energy. Surge protection for these levels is not easy to design and build. To put these numbers in perspective, the energy in one stick of dynamite is about 1 megajoule. The HEMP currents represent about 33 sticks of dynamite, and the SREMP currents represent about 130 sticks of dynamite. Without sufficient surge protection, national defense installations and the general infrastructure involving electronics will be at significant risk, not just for upset, but actual catastrophic damage. Significant effort has been devoted to designing and building this surge protection for our ground-based national defense installations,